Welcome everybody to another live stream for engineers with ideas. Today we're very excited to deep dive into the world of glass in structural engineering, which is a topic that I know a lot of people were interested in hearing about, and we have managed to find a specialist. So this is Graham Coult, who I'm very interested to hear everything he's got to say. So Graham, I shall leave the floor to you. Can you take it away?
Great, thanks very much, Dominic, and thanks for inviting me to talk. So it's a pleasure to talk to you all about glass today. It's something I've been involved with for some time, but I will shoot through this topic. There's quite a lot I wanted to include, but just background on who I am, who we are as a company. We're Exo Callahan, as well as glass. We do all sorts of other engineering as well, through from facades down to civils. And we're 20 years old this year, so we started with three of us in 2004, and over 155 with a number of offices across the globe. And for such an office in such a relatively small office in London, our reach has always been very global. We've worked in various different places around the world with differing challenges. And that's been really useful to deliver, or been very exciting to deliver such a wide variety of interesting projects. But obviously, and what's keen to point out is that we have a wide variety of staff as well. So we've got a 60-40 split between male and female, which when I started engineering was unheard of, and 50-50 between facade and structural engineers. So we do a wide variety of work with a wide variety of individuals, and that keeps it exciting and interesting within the office. And so as part of designing with glass, what's interesting is looking at how glass is made, because unlike other products, I would say, which we use in structural engineering, once it leaves the factory, it's almost impossible to modify. And so we need to think about that production process and how that might affect what our designs are. So this is a typical float plant. This one is, I believe, in Goole. I think it's Saint-Gobain. And as you can see, it's pretty large, over 1 kilometre long. And on the right-hand side is the float line. And this is a continuous process that works for 24 hours a day, 365 days a year, and generally they run for 20 years, 12 to 20 years, without stopping, and then they're sort of refreshed and rebuilt. So they're continually producing this ribbon of glass, which is produced by melting the component materials in a furnace at 1600 degrees. And to enable that float process, which was developed by Pilkingtons, it floats on a tin bath, so it's molten tin, and it gives it that smooth underside, and with the force of gravity, that gives it its surface quality on the other side. And then that's cut on the final section of the float line into transportable panels. And typically in the UK, across the world there, a jumbo sheet is 6 meters by 3 meters. And as part of that float process, they also may have coatings on. And when the coating is applied, when the glass is hot, so that's a pyrolytic coating, and that's what we call hard coatings. And they're called hard coatings largely because they're very robust and they're resistant to scratching. But because they're put on the inline process, the choices are more limited than the soft and semi-hard coatings, which is a secondary process, which is done in a magnetron, where metals are vaporized and are deposited on the glass. And these coatings are often to do with light transmission, energy transmission, to sort of handle the environmental factors. To add strength to the glass, so when strength is produced in the float line, we get a glass which is called annealed, and that means that we're trying to take all the stress out of it, although it can have a small amount of stress, sort of 2 to 3 megapascals. But tempering is the process by which the glass is heated up just past the glass transition temperature, and it's cooled down quickly in the quenching furnace with air. And this locks in stress into that panel, and I'll talk a bit more about that later. And this affords a glass with greater strength. So the surface is typically around, will fall about 120 or 160 megapascals, so a much stronger piece of glass, but it does have its drawbacks. We can also shape the glass, and again, these will be done in furnaces of various sizes, and hot bending is really limited to annealed glass, so we're taking the raw float glass and then heating it above a surface. It might fall into a mold, or it might be rolled over a mold. But again, we're heating it up to the glass transition temperature, so it starts to flow and then cool down slowly. So again, not locking in any stresses. We can also hot bend and temper. So this is the same process as the sort of flat tempering furnace, but as it comes out of the furnace at 600 degrees, and as it goes into the air quench, rollers bring up the edges so it can be curved before it's finally cooled. But increasing strength. So when we're increasing strength, what are we doing? Well, if we take this small diagram on the left, and the dotted lines running down are really relating to the length of the glass. So as we heat it up, like most materials, it's going to heat up, and it will at 650 degrees, it will soften slightly. It will also expand. When it comes out of that furnace and it goes into the air quench, the outer surface of the glass is cooled back down below that glass transition temperature. And while the inner core cools at a slower rate, that then pulls in the outer glass, creating this tension on the inside of the glass and compressive crust around the outside of the glass. And if we look at the sort of stress through the sections of glass, on the right-hand side on the 3 diagrams, we have a heat-strengthened glass and thermally toughened glass. So again, we have showing about 50 megapascals in the heat-strengthened glass and 120 megapascals in the thermally toughened glass. Finally, there's one other process that we won't really dwell on, and that's a chemically tempering process. And that puts a very high stress in the glass, typically 200 megapascals, but it's a very thin coating or very thin compressive crust of sort of 30 to 300 microns. And that's used much more in automotive and transport vehicles and trains, as such like, for their windshields. But as I'm sure you're aware, that tempered glass, because it's got so much strain in the material, that when it breaks, it releases all that energy. And so when we're looking at that, if we look at a beam in the top right-hand corner, we can see that same stress profile as we had on the previous slide. But as we're bending that beam, those profiles change. But once a crack penetrates through the compressive zone into the tensile zone, that means all that energy is released, and we get these broken cuboids of glass. And what that means is that the glass is failing safely, and historically, in inverted commas, that's being classified as a safety glass because it fails safely. But now, as we're getting, as the industry is becoming much more aware of this, is that, well, if this glass panel is in a facade, a great height, then that falling glass has considerable kinetic energy, and some of the tempered glass can form into clumps. As you can see, just underneath at the bottom of that telephone box, there's a sort of large panel that's fallen as a single piece, and they can be particularly dangerous. And so there's much greater consideration about using glass at height, and there's lots of documentation there. For example, the guys in the CWCT, Sensors for Windows and Cladding Technology, that provide greater advice about this, but I won't go into that in too much more detail. And the tempered glass might not just be breaking from a fracture or an impact. Nickel sulfide inclusions are also present, and I think about 20 years ago, maybe 25 years ago, this was much more common as the quality of the glass, as the level of impurities in the glass was higher. And the processors, or the flat glass manufacturers, have gone to great lengths to reduce these nickel sulfide inclusions, and the possibility of these nickel sulfide has dropped. Nevertheless, not all manufacturers are the same, and they're still present in glass in a quantity, and so failures are still occurring, and we must be mindful of this effect, in the fact that a glass, it does not sit on its own for an unintended period of time. There is also always a possibility that that glass breaks. So as part of being a responsible engineer, we need to look at what those consequences are of a failure. So yeah, glass is an elastic material. It has no capability for deformation or permanent deformation, and so as soon as it's reached its elastic limit, it will break. Unlike steel, which can plastically deform, and we can then start to see from steel structures when they start to fail. And this is a particular issue in glass that we need to think about really quite clearly, is that we have pure elastic material, one which can fail at any particular time, whether that's due to damage or nickel sulfide. So how do we build things safely and with resilience? And that's largely through lamination. And so this is, I think it's a 50-meter long glass staircase in Hamburg, which is an Apple store. And this was, I think, the first time we designed a 15-meter tall staircase. And this is five sheets of glass. And so what we look at is, well, if one sheet of glass breaks, can the rest of the panel support the same load? So providing some redundancy. And this is where I'd like to use interlayers. And so interlayers, over 25 years ago, used to be very simple. This is the temperature and load duration for a Young's modulus of PVB. And as you can see from the graph, as the temperature increases and the load duration increases on the far right axis, the stiffness drops down to almost zero. So if we're loading at 10 degrees in 1 second, we're getting a Young's modulus about 25 megapascals. But as we move out, we're getting much less. But over sort of 23, 24 years ago, we now have a modified PVB, which is much higher stiffness, both at its low temperatures and low time durations, but up to sort of 24, 30 degrees. We also have Carrare's ionomer material, which has lower stiffness in the shorter term, but much greater stiffness at elevated temperatures and elevated times. So it's a really useful product where we require greater stiffness over a length of time. Thanks. And this is one of the early tests we performed with the Apple design, which was 4 sheets of glass acting as a tread. And what we did was broke through all those sheets of glass and added sandbags on, so we had a long-term duration panel. And you can see that it's carrying a significant amount of load. So this tread was actually 2.5 meters wide, and it's about 300 millimeters depth going to the screen. And it's carrying a significant amount of load, and with all the glass failed. And that's because the interlayer is really acting as a catenary or a tensile bridge across the glass. Although the glass is shattered, and broken, it's still acting in a compressive manner. So adding, great level of resilience. And so this led us to build some very exciting structures. So I'll run through a few of them now. And this is quite a story about working with glasses of a particular size. So when we started designing this structure in Midtown New York for Apple, we were really limited on the sizes of glass that could be procured. And as you notice, perhaps hopefully you can see on the elevations or the walls of the cube, the panels are split into 3 sections high, and the fins inside are actually full height at 10 meters. And this is because we were just limited on the sizes we could procure and B manufacture. What we did, and so we came up with this idea of splice laminating the panels. So this is the internal frame, and you can see that the roof panels are split and they're joined with steel fittings. But the columns are manufactured from just over 6 meter tall panels, but they're cross laminated. And if we look at this next slide here on the diagram on the right, you can see how those panels are overlapped. Similar ways in which you might cross-laminate timber. And our approach was that we thought the interlayer would be stiff enough to provide the shear resistance between those panels. But as this was our first consideration, we also bolted through the glass panels to provide that shear capacity. And it's interesting to note that while the current autoclaves, which you use to laminate the glass, weren't available in the architectural industry, these panels were manufactured in the aeronautical industry in a fabricator for planes and wings, which are often composite. But as ever, as the industry moves forward, this is an autoclave being delivered to Sealy. Things improve in size, increase in size, and in Georgetown in Sydney, this was increased to a 16 meter tall facade, because we could now procure glass in 8 meter lengths. And again, we're still cross-laminating the facade panels and the beams. But a big change that we had in Sydney was that we were further comfortable with the glass and the lamination acting as a shear component to transfer the loads between the glass plies. And it gives quite a clear appearance. And this sort of level of technology improvement has always led to looking at how projects can be improved. And in 2011, we were asked to redesign Fifth Avenue because although it was highly technical at the time, Steve Jobs was, much preferred the appearance of minimal fittings. And so with that new availability of bigger furnaces, bigger tempering plants, and improved technology, what was a cube, which was made from 106 panels, was reduced down to 15. And in 2014, excuse me, and in 2014, we built a similar structure, but from only 5 panels. So we laid the wall panels on their side, and we actually used a carbon fiber roof to span between the glass walls and provide the lateral stability. So you can see that the difference between quite a fitting heavy structure, although I quite like the fittings, and you can see the function of the glass and what the load paths are, to something that's quite much more transparent, and the fittings are doing everything, so it's a bit more difficult to discern what they're doing. But these are also laminated within the glass, so you also have this completely smooth exterior, which when you're looking at it obliquely, as it sort of is in the right hand photograph, you can really get this appearance of minimalism. And more recently, we've just completed a rebuild of this store. So this was only possible because working with a manufacturer, they developed the curving and tempering process to enable this to be fabricated. So this is in Shanghai, and these panels were 13.5 meters long. And when we started out looking at this project, we had all sorts of ideas about cross-laminating curved glass. But the difficulty with curved glass is that it's very difficult to get the same level of tolerance as for flat glass. And so we ended up with something that was rather either fitting heavy or something which might have quite large gaps in the interlayer or variations in the interlayer. And so speaking with the manufacturer, they said, well, we've got this idea for a furnace which is a continuous curving furnace. And so they made this was made possible through advancement in technology. And so this is made of 2 sheets of 15 millimeter glass in the facade panels, and the internal structure supports all the vertical weights coming down to the plaza level. And the little diagram on the right shows you that in a bit more detail. So we can see we've also got a curved central ring, which is bringing together all those beams, and so we have this sort of open sort of central oculus at the largest panel we could. But just this year, it was rebuilt in a much more elegant way, and I think this is our most ambitious design to date. And so it completely takes out all of the internal columns, all the internal beams, and it's really just the same volume and the same shape, but built from a skin of glass, if you like. And so that we've got this quite flat dome at the top. We have this steel ring, which contains all the thrust loads within that ring. And then it's like a plate just sat atop the glass. So again, the glass walls are providing all the lateral stability, but also providing the vertical support now, which is quite an achievement, and it's absolutely beautiful. So again, if you come from the left, what we have is quite fitting heavy, or very much more fitting heavy, and we end up with something that has just a wonderful appearance of and sense of clarity on the right hand side. And I think that the difficulty is that the engineering involved in doing such simplistic things is really quite incredible. It's very hard work, and so I don't think these images really show it justice. It's trying to get something that's very getting to the most simplistic thing is often the most challenging thing to do. So yes, you can see quite simply how we come from what was 14 years ago, the sort of height of technology we could, or design and technology we could do, and what we started to do. I think it was back in 2020 when we started the design process. And I just want to lead up to a slightly larger project, which is Steve Jobs Theatre. But working with clients like Apple has enabled us to, as a design team, it's been a close-knit team. So it's always been, looking at what the next thing will be and how we progress the knowledge from what we've already achieved. And as you can see, this is a fairly systematic progression through time. But back in 2017, Foster's came this sort of ambitious design of putting a roof solely on glass, which was almost 50 meters in diameter. I think the glass is 43 meter diameter. And not only is it just a roof, but we have lighting, we have smoke detectors, there's PA systems and all sorts in that roof. And so fundamentally, how do we get all those things up there without interrupting this sort of glass support? We originally looked at having a steel system, and we refined that down through digital design techniques. And this was quite early on in the stage of using Rhino and Grasshopper and routines to minimize the use of any material. But in the end, we went with a full carbon fiber solution because it gave us the least amount of load to put on the glass, but it could also deal with the thermal differences better, or it would negate the thermal variations in materials that we'd have had with steel and carbon fiber cladding. And so this is just an entrance onto that goes into Apple's sort of presentation theatre space. And like many of these projects, there's a lot of collaboration that goes that is part of this between the different engineers. So Arup, structural engineers, were responsible for the overall building, and we're inserting this glass structure within that. And this is built in California, which is a seismic region. And so we have the green part, which is a carbon fiber reinforced polymer, which was initially designed by Gurit and then transferred to the fabricator PCT. And between those two, we're providing the structural systems to support the glass and fix back to this concrete ring, which was then on triple pendulum dampers. And so we had to build a system which was which accommodated both the accelerations provided by the concrete ring and the roof. And so our simplistic idea was really that the glass is transferred into the center of a glass panel, and that would share the glass load back down to 2-point fittings. And when we come to the lateral to stability, that lateral force, as indicated by the shear arrow at the top of the panel on the right-hand side, goes to this force couple of tension and compression. But what was novel, well, many things novel in this design, but what was different, certainly for the city and those who are checking our calculations, was that we wanted to restrain this panel not by mechanical fittings but by structural silicone, and that's in itself very unusual, and I'll come back to that in a minute. But looking at what we tried to do was, when we look at these models, and particularly when the analytical models get very large, is how is this in effect working? And this was a structural model we built to help translate or communicate how the system is working. So in the same sort of way, we had sort of the diagram showing the responsibilities. We have the roof mass, which is sitting on the glass wall, and that is restrained to the isolated ring slab, and that has some damping through the fixings. And that isolated ring slab, it has double pendulum dampers. So I said triple pendulum, but it's the double pendulum dampers, which are sitting on the substructure, and that's moving around according to the seismic criteria. But structural silicone is generally for sticking windows on buildings, and so this required a particularly tactful approach with the city in how we're presenting our design, and making sure that we're talking to them at the appropriate time. And this goes with any code review system where you're trying to do novel things, is it take them long for that sort of design process so they're incorporated and can understand what we're doing. And so as part of that, we did some testing on the silicone, and this is a straight pull test. But what we're doing this pull test is we're cycling the load, and that means that we're pulling, releasing, pulling, releasing. And this is a small graph I won't go into in a lot of detail, but this is a time history graph, which, if you look at the bottom left-hand corner, you pull it, and then as the load is taken off, it's not coming back to point zero, it's moved slightly along the graph. And what this is essentially showing is that as this loading and unloading takes place, the silicone is softening. And when we went back to Dow, who were the manufacturers of the structural silicone, they said, "Oh, we don't know why that's happening," because Dan been asked this question before, but because silicone was really used to bond glass into windows. And it turns out it's something called the Mullins effect. And this was related to me by one of the Dow technical engineers, is that, it's when you have a rubber balloon and you're about to blow it up, you stretch it a couple of times, it's much easier to blow up. So the material's relaxing. So once we understood that, we could then sort of finalize the design, because obviously having something that's less stiff changes the performance of the material and performance of the system at whole. Now, if we're looking at the sort of unwrapped elevation, so this is glass unwrapped, we have the loads being transferred back down to the floor fixings, or the fixings back to the concrete. And what we did there, so this is a blow up of the detail, is we have these orange blocks which allow compression through. So as the roof is sliding one way, we can take compression on one side of the panel, but on the other side of the panel we're having it lift up. And had a request from Arup looking at the system. What they said was, well, it's an fully elastic system. We want this to act plastically. And so what we then did was, okay, we put in what we call a fuse element. And so once a certain amount of load is introduced into the glass, past its design point, or says, okay, before we pass the design point and before the failure point, what we'll do is we'll allow steel to yield. So this gives it another level of resilience if the design criteria are exceeded. And so we could tune this. The reason why it's sort of throated down across that plate is so we could tune the level at which that goes plastic. So as you can see, the arrow goes up, and then we get 4 plastic hinges as that moves up. And this is some very early FE analysis. And you can see that we're yielding at a factor of 1.1 of the design load, and we're fully plastic at 1.6. Hopefully this video will work. Sorry, I should say that the previous slide, this is a test construction in Dubai at PCT's, or just outside PCT's factory. And there's 30,000 bolts which go in to fix all these elements together. And it was Dubai Summer, so it was incredibly hard work. But it's a qualification of the stiffness of the system. That was really important for that design. So this is on site in California. And so it's built on that rig. You can see at the bottom of the panel on a substantial crawler, and then lifted over. It was interesting also to note that this loading condition, as in the negative loading condition, was one of the worst cases. Unfortunately, the camera fell over, but you get the gist of it. But it resulted in a fabulous structure, really quite beautiful, and all the surfaces are just running up in between the gaps between the glass panels. So there's nothing really to interrupt that. And while we're talking about transparent things, it's a slight departure from glass, but I think it's worth including, because we were approached because the intention was that this should be glass, and this is the Sky Pool in Nine Elms in London. You can see the US Embassy, or the rendering of the US Embassy above, and Hal from Hal Architects asked Brian, said, can you come and help with a pool I'm looking at? And so we started having a look at this pool, and it was I mean, before I start, when it first hit the newspapers, I was actually on holiday, and it made the news quite quickly all the way down to Australia, as we can see in the CNBC. But it was of huge interest, and it's a lap pool, 25 meters with a 15-meter span in between the buildings, up at 10 stories, and we have 2 steel tubs at either end. We considered using the same material all the way through, but as underneath the end panels, you have the plant room, so there's no real point in looking down into the plant room. So we used no paint material. 150 tons in the central span, considerable amount. 15 double-decker buses, if that didn't seem large enough. So a considerable challenge. And so, as I said, that we originally looked at glass, and this was one of the first sketches. And from a structural standpoint, that there is a logic to this, and we have floor panels, we have glass beams, transferring that load into the edge wall panels, and then because of the hydrostatic pressure of the glass, we introduced the consideration of having a glass edge beam to take that lateral force. But and this is the sort of part of working with glass, is that, well, how do we join those floor beams into the wall panel? And if we take this simple diagram, we've got compression and tension. I think we should all be cognizant of that, is that because glass is purely elastic, the stress will not easily flow around the hole, and that stress increases. So because that hole cannot form, or they cannot plastically deform, you have this the stress increase around the hole, and that's typically 3 times the stress in the body of the glass. And after doing a few calculations, very simple ones, is that we're talking 10, 12, 13, 14 sheets of glass for that wall panel. And while glass is a great material, it can chip, it can crack. And the consideration of what happens if there's small damage in one of those panels would be a very difficult replacement. But also glass at that thickness tends to it increases in color, and it drops in transparency. So my mind was brought back to sort of some projects I saw earlier in an aquarium. It's actually an Osaka aquarium that brought back to mind, and they were sort of 10, 12-meter walls. And these weren't the aquariums, but 10 to 12-meter walls, and they're made of acrylic. And the benefit of that is it could be cast to the thickness required, and with a consideration of safety, if we're using that for life preservation, sort of for deep sea submersibles, I thought, well, there's no reason why that we can't consider this for such a pool. And so again, that much like glasses, we have to look at what are the movements, what are the accommodations of building movements we need to accommodate. And what we also need to do was remove any fixings, or remove fixings that were in the acrylic, because acrylic is relatively soft. What we didn't want to do is bolt the steel tubs onto the acrylic. So what we decided to do was have a tendon that pulls those tubs onto the acrylic. And so it's a compression-only joint through there. And to prevent that being pulled apart, the tendon serves as that purpose. I'll just skip through some fabrication photos because it's so interesting. But this panel in the picture is about 8 meters long, but you can see from its level of clarity, it's absolutely amazing. And you would not get this with glass. Because of the size of it, they had to build an external oven to autoclave and to heat up, and not to autoclave, to reduce or to heat up and cool down the acrylic during the bonding process. A lot of handiwork went into this. It's certainly not say, a machine-made thing. That it's a manual. It's an art, really. And this is one of the early visual assessments of it, just out in the yard, and you can see some rippling in the acrylic, largely because it's a handmade object. But we weren't that concerned with that, because as you've got water sloshing around in it, that would be imperceivable again. So it's loaded onto a trailer out in Grand Junction, Colorado, and it went out to a port in Texas, where it came into London. Had a little trip on a tug down the Thames before it going on one truck to deliver it to site, and then being lifted into place on site. And it's a really marvelous thing. I'd say if you've got a chance to go and see it when you're in London, do, because it's really fantastic. And I guess kind of more about the sort of the core ideas of designing with glass. I know I've got 15 minutes left. I think the Eurocode is available as a technical specification now, and designing with it has, as I said, we're designing robustness and the consideration that something might fail. And so there is different ways of looking at load considerations and limit states. And so the consideration is, a glass may fail at any particular time. And so what we used was this idea of a workman on a glass panel on site, and a hammer could be dropped and it breaks glass. So as we went back earlier talking about the toughened glass, if we just have a single sheet of monolithic glass and that breaks, the person will fall straight through. There's no residual strength for that. Now for laminated thermally toughened glass, and I would say depending on the interlayer that's being used in the edge conditions, is that the glass may well break, and both sheets may well break, but the panel may rip or tear from its fittings. However, for things like heat strengthened glass, which doesn't have the same amount of energy as thermally toughened glass, it will break into larger fragments, and so that provides it resilience for a greater period of time. And so the operative can then has time to step off, and this can be read a little bit more in our article in the Structural Engineer, which is February 22. And a big part of what we do, I think, is really important, is particularly, with glass, and we've always had a very close connection with the fabricators and clients with glass structures, and more so more recently with lots of other materials as we're involved in structures, general structures, and facade engineering. Is that engineers declare has been a big part of what we do, and it's about what can we do to improve how we work. And I think that what comes out of that is this what consultants haven't been good at in the past is being cooperating with each other and sharing knowledge about carbon intensity and how we look at reducing carbon in our buildings. And I think that's a really important point. And I think that we really have to be mindful of that. And we've launched, we've used, and we've got tools such as Eco, which is a Revit plugin, which we encourage others to use. It's not something that's only internally. But we've also done a lot of work in understanding on the glass side what the supply chain looks like, because when we started the research 3 or 4 years ago now, is that such a small percentage of glass was being recycled, largely because it's a commodity. It's made from sand, which is pretty ubiquitous. And so the effort to recover glass from building sites or residents is quite high. So it really just gets landfilled. So I won't go through that, but yes, please read about that more in the Structural Engineer. But one thing we did do and we're really proud of is we've launched a website called Glass Recovery, which really takes all that information and puts it in a much simpler context, more accessible to everybody. Those who are installing and deglazing, of how they can take responsibility for what they're doing and recycle more glass. And so we've rebranded all our diagrams, and we've published this online, and we're asking collaborators to sign up. We've had a lot of help across the industry, including consultants such as Arab and Thornton Semisetti. So, as I said, it is about collaboration and working together, because we don't want to run a website that is solely about a glass sector recovering more glass. We're consulting engineers, so it's about sharing these and trying to do better than we did yesterday. And at the heart of the functionality is really enabling people to find who will be able to reclaim the glass from a particular building project, and providing advice on what glass can be recovered. So yeah, please get involved with that. And probably lastly, I'm involved with CROSS, which is Collaborative Reporting for Safe Structures. And this is a really valuable tool or valuable service for recording near misses and problems that we see in design or on site, anywhere, for projects we are involved with or not involved with. And it's got an international network, and that it works closely with the building safety regulator. And at the moment, that we're working with reports that are received, particularly on the right-hand side, where we have voluntary reporting, and that comes from all members of society. And so I think that if you see anything that you're not happy with, or you think maybe an issue, and perhaps if you're not able to tell your superiors or whatever, I would just say, please send in a report to the CROSS, and it is anonymized. So I and many others review the reports. They are anonymized before they even reach us, and so it's a way of sharing the problems that we see with the wider community. So we learn from mistakes rather than brushing them under the carpet. As I said, it's confidential. It's really simple to do, and it doesn't take a lot of time. But obviously, that we're dealing, anything which involves fatalities has to be with the regulatory authorities. But that if there's anything else, please get in touch with CROSS. But as I said, that can happen through any stage of their sort of design construction life cycle, right from design all the way through to decommissioning. And you can find the reports on the website, social media. If you sign up, you can have the emails just drop straight into your email box. And it's very simple. So yeah, please get involved with that, and help us spread the word of where we see problems in the industry. And that is my last slide. So I think 5 minutes to go. Not bad.
Perfect, Graham. Thank you very much. That was fascinating. Really was fascinating, talking about the projects and then kind of going on to the manufacturing process. I think I certainly learned a lot there. Which just leads me to say thank you so much for your hard work and effort for putting that together. It's been amazing having you on as a guest. And to all our viewers as well, we will reach out just to see what you'd be interested in for your next topics as well. But it just leaves me to say, Graham, thank you very much for coming on.
Great. It's a pleasure, Dominic. Thanks very much.
Take care.
Okay. Bye-bye.